Hello everyone, it's August 12th. Alright, yesterday I forgot to get the microphone to work, so we have no mic. Oopsie doozy. But today we'll have a microphone, so everything will be fine. Check if there is a valid partition for the array. You're given a zero index integer array nums. You have to partition the array into one or more contiguous subarrays. We call a partition of the array valid if each of the obtained subarrays satisfies one of the following conditions, because there's exactly two equal elements, exactly three equal elements, consists of exactly three consecutive increasing elements. That is, the difference between adjacent element is 1. For example, subarray 3, 4, 5 is good, but 1, 3, 5 is not. Consecutive increasing element. The difference between adjacent element has to be 1. Return true if the array has at least one valid partition, otherwise return false. So this first one is true because we can partition into 4, 4, and 4, 5, 6. Okay, so looks DP to me, right? You have an array, you have A0, A1, A2, to AN, right? So immediately we can say this is whether true or false, right? So the DP index gives you true or false, starting from index to the end. So we say, okay, I want to start this to the end. So we will see, is this possible? If it's possible, then will be this. And if this is possible, if it's possible, then this to the end. If at the beginning I cannot form, then it's just no good. Okay. All right, let's write this. All right, so what we will need a DP, int this memo, right? We need a memo. Memo equal to new int. Yep, I remember we should use integer. Nums dot length. Okay. Then we don't call DP here. Int private int DP int index. Right. Again, if index is equal to yeah, I'll use this trick. Int nums. Nums this dot nums equals nums. Okay. And then I say if index is equal to nums dot length, shall return true. Right? Because we're asking. Wait, hold a second. Empty array. What is an empty array? Yeah, we should return true because it shouldn't really matter. And this is Boolean. Right? It shouldn't really matter. And then otherwise we say if memo index is not equal to null, right? Then we'll return memo index. Otherwise, oh yeah, that's correct. This is not integer. This is Boolean. Oh, do we have Boolean? Yes, we do. There we go. Okay, so now what? Now we're gonna say for the current, I want to see if we have only one left, right? So it probably can handle it here if this is equal to this, or we can just say if it's larger or equal to -1, that will Oh, hold a second. If it's equal to this, return true, right? And then we just say if we don't have enough, right? If we only have 1, then we should return. If index is equal to nums dot length minus 1, return false, right? That's only 1. We have only 1 left. That's always false. Now we have at least 2. Then I can say option 1, 2, right? 2 are the same. A triple, a double, a tuple, an identical tuple. We say if nums index is equal to nums boolean res equal to false, right? We can actually say memo index equal to false. If this is equal to index plus 1, then memo index will be all equal to dp index plus 2, right? Index plus 2. Option 2, triplet tuple. If nums index equal to nums plus 1, if index plus 2 is smaller than nums dot length, and this and nums index plus 1 is equal to nums index plus 2, if that's the case, memo index or equal to dp index plus 3. Option 3, concept triplet tuple, not identical triplet. Consecutive increasing triplet. If index plus 2 smaller than nums dot length and nums index plus 1 is equal to nums index plus 1 and nums index plus 2 is equal to nums index plus 1 memo index or equal to dp index plus 3. Well, we can actually put these two together. If this and this or this, right? So if this and this or this, this shall be from here. Get one up. Okay. Right. Option 2 or option 3. Right. Once we're done, return memo index. Okay, and we just return memo, not memo, dp 0. Alright, let's give this a shot. Press the wrong button. Is this alright? Yep, looks okay. Oh, I didn't test the 2 situation. Well, I guess it's fine. Okay, so this is the pretty naive DP. Pretty naive DP in which DP index is whether it is possible to partition nums index towards the end. ON. I mean, we did 3 times, but still ON. So what this tells me is it's possible that we have a better solution. It's possible. Hold on, let's get this one up first. Maybe we can try bottom up, right? We can try bottom up, and if we try bottom up, maybe we'll find a, slightly better solution. Okay, bottom up. Basically, we have a DP as well, right? This one will be false. Okay, the last one will be false. We'll do one more, so that this one will be true. Okay, this one will be false. So for this, what we want to do is check if these 2 are equal, right? Check this too. If these 2 are equal, then I will say it's true. If these 2 are equal, it will be equal to this. If they're not equal, we can actually check another equal, right? Yeah, we can do bottom up. Let's see if bottom up will make it faster. So I'll do bottom up. I don't need these things. Okay, I'm gonna try bottom up. No memo. We'll say DP. We're still memo. No, we'll call it DP. A new boolean, right? DP equals new boolean nums.length plus 1, and DP nums.length equal to true, and DP nums.length minus 1 equal to false. Okay. Then we say for int I equal to nums.length minus 2, I large equal to 0, I nice minus. If nums I is equal to nums I plus 1, dp I shall equal to dp I plus 1, I plus 2, right? And then if I plus 2 is smaller than nums.length and nums I plus 1 is equal to nums I plus 2, in that case dpi shall I think all of them should be this. It's actually, that will be the first one, right? All equal to dpi plus 3, right? So that's first. Else, if they're not equal, else if they're not equal, and else if I plus 2 smaller nums.length and nums I plus 1 equals nums I plus 1, and nums I plus 2 equals nums I plus 1 plus 1. Right, if that's the case, then dpi should equal to dp I plus 3. Okay. And then if this doesn't, then we just don't set the current, which will remain false. Just fine. Now I return dp 0. Okay. This one, right? Oh, bottom up is, now that's why we have to do bottom up. So from previous days of experience in Java, bottom up is faster, much faster than top down in DP. I guess in Python it's never really an issue. I remember the performance is pretty similar, but yeah, Java looks like to be slightly different in this case. Yeah, it's all good. We have to practice no matter what. Go to solution. Bottom up, top down. Yep. Space optimized. Oh yeah, you don't even need to have this whole thing. Holy crap. You only need 2. Ah. Yep. One more round. Bottom up with space optimization. No need to create an array. All we need is 2 additional values. Right, that is to compute dp index, right? We need dp index plus 2, right? And dp index plus 3. So we get these 2. dp plus 1 plus 2. This is dp plus. Good memory. After I might forget. Huh?
It's too late. I don't know how to put it on the bike.
I'll put it on.
Sorry, I was asleep. Before you go to sleep?
Maybe you'll fully charge by then. Wait, where's your light? Got it. All right, I'll get them charged. All right, where are we? Oh, we're gonna do optimized. How do we optimize it? Which is a true value, right? True value. So at the start, we have this, and we have this.
Here.
I got it. All of them. I need 3 values. Yeah, I need 3 values. Which is, call it Boolean. Next. Boolean. Ugh. Next. Next, and next. Oh, it sounds so stupid. So next is going to be, because I start from this one minus 2, right? I start from this, so the next shall be false. Okay. And next shall be true, and next shall be true. Okay, so and because it says at least 2, so it's fine. So yeah, -1 is 2. So if this is equal, right? If these 2 are equal, then that shall equal to current. My goodness. We also need a current, Boolean current, right? So if this, then current equal to next, right? Current, next. If this, then we say current all equal to next. If this, then current equals next. Once we done, we need to reassign them. Oh my goodness, how do we reassign? How do we swap? We need a temp. Ugh, that was ugly. That was ugly. So basically, oh, we don't need, we just say next equals current, right? No. Next equals to next. Next equals to next, and next equals to current. Something like that. Okay, let's initialize it every time. It's okay. It does not matter. We will initialize it before. Okay, this one equal to false. And then every one will be this, and then this. Okay, and at the end, the next. Okay, let's see. That's right. It's alright. 7.6 milliseconds. It's about the same. It doesn't really matter. But we do have 01 space complexity. Right, that's what we want. That is what we want. Solution 3. Okay, so that's it. That's all of it. Oh. Yeah, you can do that. Alright, move on. Minimum cost to make all characters equal. All characters equal. Zero indexed binary string of length n on which you can apply two types of operations. Choose an index I and invert all characters from 0 to I inclusive, which will cost I plus 1. Choose index I and invert all characters from index I to the end inclusive with a cost of n minus I. So the cost is just the total number of operations, right? Because 0 to I is I plus 1. And from I to n minus I, from I to the end, so n minus 1 minus I plus 1, yeah, n minus I. Yes, that makes sense. The minimum cost to make all characters of the string equal. Very interesting question. Very interesting. So we have 0, 0, 1, 1, right? So I can say I can start from here. Oh, we have to do multiple times. Multiple times. Interesting. Hold a second. All right. How many steps? Well, not how many steps, minimum cost. Minimum cost. So we can go high cost and it will always work, right? Yeah, we have to flip. We have to flip. I mean, we can think if we don't flip, Like if we flip something, like at the end, right? At the end, it has to be all ones or all zeros. And if you flip, huh? Interesting. The minimum cost. Well, I can say the minimum cost overall, but it could be, you can do it multiple times, right? You can do it multiple times. Hmm. I have to try some stuff just to see how it goes. I mean, if you start from the start, then nothing will change, right? Because 0 and 1 is two different states. If you start from the start, just all the 0 become 1, all the 1 becomes 0, so nothing will change. So you don't want to start from the start. You start from somewhere. Okay? You start from somewhere. So let's say I want everything to become 0. So you start from this, and you turn this becomes 0, 1, 0, 1, 0, right? And after this, you change this 0, 1, 0, 1, 0, 1, 0, 0, 1, 0. That will take 1, 2, 3, 4, 5. Nah, that's like 15 steps. That's just one by one, right? One by one. But this is saying you can do it better. How do you do it better? Okay, so if it's by itself, we don't have to do anything. If this, we don't have to do anything. 1, 1, don't have to do anything. So what if we have like a 0, 1? 0, 1 is the same as 1, 0. So you just need to consider 0 something. If it's 0, 1. If 0, 1, then you change 1, right? Boom, done. Now we have 3. Okay? So like 0, 1 and 1, 0, both are need to take 1. This is take 0, right? So 3 we have 0, 0, 1, 0, 0, 0, 1, right? 1, 0, 0, 1, 1. And then 1, 0, 0, 1, 1, 0, 1, 0, 1, and 1, 1, 1. So this is 0. This, because these two are the same, so this will take 1, right? Which is just would go left. So this is also 1. And this is also 1. This is also 1. Okay, so how about 0, 1, 0? 0, 1, 0 should be 2, right? Because I change I change this 0, 0, 1, then 0, 0, 0, 2 plus 1, that's actually 3. But I can also do, I just change this one, 0, 1, 1. Change this one, 1, 1, 1, so it's 2. Because one step's definitely not possible, so this requires 2. And this requires 2 as well. Trying to see if there's any pattern out there. Alright, how about 4? Alright, and then again, this is 0, this is 0, right, this is a 1, this is a 1, this is a 1, this is a 1. Okay, for the remainder, yeah, this will be 2, which means this will be 2, right? So remainder is just them all mingled. Like, I know this will take 1, but you add 1. Yes. Alright, back at it. If I know, yeah, basically the question, like, if I know 1, 0, 1, 0, right? This will take 2 steps. Now I add another 1. Can I compute based on what we know before? Like 0, 1 requires 1. Or like easier, like we 0, 1, right? We know 0, 1 require 1 step. Now we add a 0. Okay, now we add a 0. So 0, 1 require 1 step to become the same. So whatever it becomes to, if, because, oh no, it's because it can go this way or it can go this way. It's affecting. Not. I think it changes state, right? It changes the state. Probably not. Interesting. Can we say this whole thing, because we choose some stuff, right? Then we'll basically change one side and the other side remains the same. And once we change one side, like if we change one side, like if we change this one side, then we change again, then it's the equivalent to change this side. You know what, let's take a look at this one more time. 0 1 0 1 0 1. I think the first operation I equal to 2 0 1 2. So will be, so first operation is here, so it'll be 1 0 1 1 0 1. Okay. Second operation with I equal to 0. No, first operation is 0. No. First operation I equal to 1. So I change to 0 1 1 1 0 1. And then operation here 1 1 1 1 0 1. Then option 4 is this one 1 1 1 1 1 0. And operation 5 1 1 1 1 1 1. You see, when we change, we never change again. Like if we change this in the future, we never change this again, because that means this part basic is not changed. We might as well just do this and this, right? We can save. So wherever you do, you're always going to be change and then change and change. So they will never overlap. Okay, that's a good observation, right? Because overlap is always making things worse. So we do not overlap. So basically, let's say we start from some position and then we change to the left, and we start from some position and change to the right. That's how we're going to do it. Okay, so if that's the case, in this case, I've changed here to make everybody 1. So I change here, make everybody 1, change here, make everybody 1. Okay. And then we change here to make everybody 1, change here, make everybody 1. Can we summarize this? I think that is how we're gonna do. Like we can, you know, maybe we count the number of ones and number of zeros, and one of them I have a majority, and then I think it's because at the end of the day, what we want to do is not to change one thing over and over again. Like here, you see this one, right? This one's original 1, but we have to change to 0 and then change back to 1. So we want to avoid doing that as much as we can. Okay, if we want to avoid doing that as much as we can. We want to look in the middle. Okay, so what I will do, I'll look in the middle and find who is in the middle. Is that a 1 or a 0? Because whoever is in the middle, we don't have to deal with, right? We don't have to deal with. So we go into the middle and we look to both sides. Well, maybe there are only 2 situations. You either turn everything to 0 or turn everything to 1. So we can say, like, in the middle, we want to turn everything to 0. Okay, so look in the middle. And if the middle is a 1, then you know you have to change that. 2 pointers. 2 pointers start from the middle. Like if it's even, right? If it's even, then we have 2 pointers perfect. Well, 1 pointer here, 1 pointer here. If it's odd, then if it's odd, 1, 2, 3, 4, 5, right? If it's odd, it can be 1 be here, 1 be here. It doesn't really matter, right? And then we can just say, okay, if we want the target to be 1, if it's 1, we move. If it's not 1, we have to change. And after we change, then we move on. We can count how many changes we have done so far, right? If it's odd number of change, then this will be need to swap. If it's even number of change, that will remain the same, right? So in this case, yeah, so this good, boom, this is 0. So now we change. Now the change time is 1, and then move here is a 1 because it's odd, right? So this is actually not a 1. It's it should be flipped. So that's a 0, right? So we want to make it 1, so we have to change again. So we have 2 changes, right? I have 2 changes on this, and each time we can record the number. So we have 2 and 3, right? Basically we have here we have cost is 3, and on this side we have to change once, the cost is 3, right? And then we move here because it's 1 change, so this one is a 0, so we change again, so we have the cost 2, right? And then when we come in here, because we're 2 changes, so it's the same, so we have to change it not 1 more time, so it costs 1. So therefore the total is 9 costs. I think this one makes sense, right? Let's go. Let's like a little bit greedy, and we go to 1 more time. So what we want is, so first of all, we have proven that overlapping change is just useless. So we don't want to overlap change, right? So the change to the left and to the right shall not overlap each other. So the left and right should not overlap, right? And that means we have to pick something, like in along the way, 1 to the left and 1 to the right, and then we're going to change that way. So when we do that, we might as well start from the center, because if we don't start from the center, then one side, actually, I mean, do we even need to start from the center? I mean, what if we don't start from the center? I don't know. Because the change, the cost is the same, right? Once you start, the cost is the same. I mean, the idea of starting from the center is we can avoid some of the changes, right? Because if we don't start from the center, then everybody was changing all the time. But if we start from the center, and then once, if it's equal to a target, then we can save. Like, this one's saved, right? This one's saved. Yeah, this one is saved. So we don't have to go through this. So we start from the center, right? And for even, it's easy. For odd, I'm thinking if we have to swap both sides. I guess we don't have to, because it's basically the same thing. I don't think we need to. And then we'll do 1 for 1 and do 1 for 0. We can try to implement this and see if this one works. Is this the best we can do? I'm not 100% sure, but I don't see how another way can make it even better. Because we are saving from the center, right? We try to, and once we start changing, then there's no way, like, things will start change. You have to keep changing, right? You have to keep changing just to get it back. But from the center, we can save some operations. So here is, sorry, pressed the wrong button. Shoot. But am I still on? Oh, I pressed the wrong button. I quit. Am I still? I guess we're still on. Yeah, I pressed the wrong button. Okay, so I don't have a good proof, but we're gonna just go for it. So basically, we need to write a function, right? We need to write a function. We call it private int. Call it solve. Okay. What do we need for this? What we need is s. We might as well just declare it outside. String s. We can say s this dot s equal to s. So we don't have to do s. Solve. We just need a target, right? We need a target. So it's going to be char target. And this one return an integer. Okay? All right. Then we're going to have the I and j. Okay, int I shall equal to s dot length, okay, divided by 2. Int j shall equal to I plus 1. Is that right? So if edge case goes first, if s dot length is equal to 1, right, then we should return cost. The cost is 0. It's always good. So now we have at least this 2, right? So 2 divided by 2 is 1. Huh. 3 divided by 2 is 1. So we'll always... Really? 1 to 4. 4 divided by 2, 2. Ugh, that was not what I want. How about 5? 5 divided by 2 is 2. I don't want it. I think what I want is this one minus 1 divided by 2. Or, you know what? Yeah, even better. I define j first. Okay? And then I will equal to j minus 1. Right? That makes sense. So if I have size is 4, 4 divided by 2 is 2. So 0, 1, 2. That's j. I is j minus 1. If I have 2, right? If I have 2, length is 2. So j is 1, I is 0. If I have 3, 3 divided by 2 is 1. So 0, 1. J is here. And I will be 0. Which is okay. So this is the starting point. And then, based on our target, we're going to go down or go up, right? So to go down, I need a count, right? So I need a swap invert count. Okay, invert count equal to 0. Okay, while I is large equal to 0. Okay, so we're gonna go down from the center, go down. We say if s dot char at I is equal to target, right? Oof, hold a second. Hold on. This is where the complicated part happens. If invert count mod 2 is equal to 0, we did even number of swap, and char add is equal to this, right? If that's the case, then I minus equal 1. We don't have to do any more additional things. And of course, we have to also define int res equal to 0. Okay. Elif else if invert count equal to 1. So it's the even number, odd number of swap, right? Odd number of swap. So basically whatever the original is will be different than s dot char at I is not equal to target. If that's the case, we also don't have to. So this is actually going to be part of the condition. Hold on. Right, this is gonna be part of the condition if this or this, right? We have to add this. So both these cases means I don't have to make any changes, right? I don't have to make any changes. I can just keep going. Else means this don't work, right? Else means it doesn't work. What does it mean? Like this is equal to 0 and then this is not equal to, this is equal to 1 and this is not equal to. So we need to do swap, okay? So if we do swap, then we do invert, then we need to count, right? So we say res the plus equal to I plus 1. That's the number of cost. Once we've done that, invert count the plus equal 1. And we will I minus equal 1 as well. Right? How are we going to do this? So if this and this or this what's the reverse of this? Reverse of this is equal to 0 and this is not equal to, right? Or this is equal to 1 and this is equal to. In this case, I will do this, right? Otherwise, I minus equal 1. I minus minus. Does that make sense? So it's even number of invert, and which means we doesn't change. And if it is not equal to, then we need to do this. Odd numbers of invert, and it's equal to, then that's bad. So we need to do invert, right? And then we invert plus equal 1, res plus. If this does not work, that means we don't have to do any invert at the current stage. Then I just minus equal 1, all the way until the end. That's good. Okay, now we're gonna say while j is smaller than s dot length. Okay, same thing. We are going to copy and paste. So if this, we have to reset invert equal to 0, right? We reset it, and this is gonna be j, right? And this is gonna be j, then rest plus equal to s dot length minus j, right? That's the total number of operations we need, and invert, and this is going to be j plus plus, right? And at the end we can return res, right? So we shall return solve 1, the minimum of these two, right? And say math dot min this and solve 2, not 2, solve 0. All right, does this one work? All right, just give it a shot. Does this one work? So far, so good. I mean, yeah, we do this. I mean, it's just the same thing. right? All right, we can give it a shot. The hell? Oh, you gotta be kidding me. Things I never have to worry before, now I have to worry. The size is fine, I can use int, but this probably is also fine, but this one, maybe I have to go long. This might have to be long. Oh yeah, it's a long. Shoot. Yep, it's a long. Pass, but with not really that good. Yeah, why doesn't this give me an error? This is an int, I'm returning a long. I thought it would give me a compilation error. Maybe it does. You just never know. Maybe it does. You just never know. You just never know. You simply do not know, don't you? Minimum cost S. Constraint. Oh, there's a thing called constraint too long? What? Oh my. How do I resolve this? Apache Common LAN. Oh. Wow. Split up and add up. Nah. That's not what we want. I mean, it's okay. I mean, we solved this. All I want is to see if the compilation will. You know what? If you want to see if compilation will pass, we don't even need to have a really long string, because compilation doesn't really care. I think I could just like do this, and I can run. I wanted this. Compilation pass. Except the return value is never used. Yeah, because this is returns an int. It's contained in long. That's why I never show you error. Yeah, I agree. This should be long, right? I think that's the only change. Oh, it doesn't matter. We'll do it over there. Yeah, not the best. Not the best, but it gets the job done. What I wonder is, maybe I just need to do one. That's what I think. No, you have to do two. Or maybe we can count. and decide. Yeah, maybe. Yeah, we can count, right? So how do I count? Java count number of chars, number of same same character in it. Do we have a fast way to do this? Ah, you gotta be kidding me. Count matches. Spring framework. Oh, that's why people need to use use framework, because it gives you so much more power. Apache, Spring. Split, filter. What's this? Dot count. Performance. Of course. String tokenizer. Why? Oh, it's by John Skeet. Yeah, I'll just count. It's fine. So what we'll do, count 1 equal to 0 for int I equal to 0, I smaller than s dot length, I plus plus, right? If s dot char at I is equal to 1, count 1 plus equal 1, right? Blah, blah, now I have count 1. Now we say if count 1 is smaller than s dot length minus count 1, then return solve 1. If count 1 larger than s dot length minus count 1, then return solve 0. Otherwise, maybe I can just say smaller equal to. Then we'll do this. Not sure. But does this really speed it up though? Because when you do the count, that's on, right? And here, that's on as well. So yeah, I don't really think it makes it any better. And I don't really have a proof. Oh my goodness. Come on, man. I don't even have a proof that this one will work. Yeah, I mean, overall it shall be exactly the same. Yeah, it ain't right. The third one. Output 5. What? Oh, yeah. That's not right. My bad. Yeah, this is not right. Now screw this. This is the one. This is the one to go. This is the one to go. Okay. Now you're gonna. Oh, it's not this one. Greedy. We can easily prove, right, that the left and the right invert operations should not overlap each other, right? Because otherwise we will conduct duplicated operations and always make the cost bigger. Thus, the solution shall be starting somewhere, right? Shall be two indices starting somewhere around the middle of S, one going left and the other right, progressively inverting all the chars until they all conform to the same. Now each time, a key observation is that after even number of inversions, the char in S remain the same as the original version, right? And after odd number of inversions, the char in S is the opposite of what it should be. This allows us to check whether a round of inversion is necessary to convert the ladder at the current position. And we do it twice, right? And then we use this method to convert everything to 1 or 0 and pick the one with the smallest cost. ON, 2n you can say, right? O2n. This is O1, ON, this is ON, O2n. It is slow, but works. All right, let's see, what do the smart people say? Single pass. Think greedy. Flip all the bits to make the string the same. Take this for this test case. First, it is feasible to make last two. Yes. Then make those require 2 plus 3. Start traversing through the array if you encounter different elements. Check from which side it is feasible for us to take less move to make it equal. either from the front or from the back. Maintain a variable answer to keep. Ooh. So we keep going. If it's equal, now I have something si is not equal to the previous. If it's not equal to the previous, I either change all the way to the right or I change all the way to the left. It's very interesting. If we flip 0 to I, that will affect. So yeah, so you go. If there's a difference, then you will flip. Because when you flip, you flip the I, so they become the same, right? And then you keep going. If now they're not the same, then you flip I towards the right. But if you flip towards the right, then on the right hand side they flipped. Yeah, if you flip to the right hand side, if you flip to the left hand side, that's fine. Okay, we either flip because I and I plus 1, I minus 1 is different. So you need to flip. Shouldn't you flip I minus 1? Oh yes, I minus 1. Yes, you flip I minus 1. So you maintain the I. So you keep going. Okay, that I agree. Or you need to flip I. Okay, so you flip I flipped. But in reality, you didn't flip, right? You didn't flip. It maintained the same. So you keep going on. The next one, if they're different. Yeah, okay, what troubles me is from the front, from the back. When you do it from the back, everything from the back is flipped. If everything from the back is flipped, so let's write it out. If everything from the back is flipped, what it's trying to say is, so if I flip from the back, right, then this one's flipped. This one is flipped. But then when I compare to this one, I still compare to this. Because the relative relationship is the same. No matter how you flip, if they originally is different, after you flip, they're still different. Right? They're still different, so it does not change. Okay. But why? Because each time you have to flip, right? And this one will allow you to maintain the longest stretch when they're the same. Yeah, I think the reason is when you do a flip, right? When you do a flip, the relationship between adjacent are maintained, right? So when you do a flip, if they are the same, so you don't have to flip. And if they're not the same, then you'll flip. So yeah, if we have an unequal, if the adjacents are not the same, so they will have to flip, right? No matter what, you have to flip. And after you flip, you just try to see if we can maintain the same. I don't know, I mean, it does make sense, but what's the proof of this? DPI is the minimum cost to make the first I characters string equal. If we encounter an index I such that they're not the same, then we can either flip the prefix with cost I or the suffix with cost this. Choose a minimum of these two. If I essentially make the first equal while maintaining the cost required. Makes sense, right? this one has better explanation though. All right, we're gonna try this. Okay, last shot, then we are going to call it a day. Not really call it a day, I still have more things to do, but for now. Inspired by, we can simply check SI and SI minus 1, right? If they are identical, we don't have to make any inversion. Otherwise, we either invert S all the way to I, or invert SI to the end, right? In order to maintain that S all the way to I are all identical. Now we choose the smaller of the two costs. Okay, we say long res equal to 0. For int I equal to 1, I smaller than s dot length I plus plus, right? If s dot char at I is not equal to s dot char at I minus 1, res plus equal to math dot min I, because this is I minus 1, right? I minus 1. And or we go from I to the n is n minus I. What's n? S dot length. Right, either flip. Oh, I already said that. And or return res. Alright, my solution also works, so at least if it's a contest, we'll have got it as well. Oh, but the runtime is very different. All right. Okay, I think that's it. All right, that'll be it. I was